In this video, I'd like to walk through a solution to exercise 44 at the end of chapter 10. You should pause the video and read through that problem so you can get familiar with the numbers. But in essence, it goes like this. There's a beam that sticks out from a wall, and you're told that the beam is 9 meters long. And you don't know its mass. But it's supported by a cable that goes up to a wall at an attachment point that's 4 meters higher than the hinge joint here. And the cable itself is 5 meters long. You are told that the maximum tension that the cable can bear is 1,000 newtons before it breaks. And in fact, the question is to figure out what's the largest mass of beam that can be supported by this cable before it breaks. So before we draw a free body diagram, looking ahead, I think that it'd probably be a good idea for us to figure out what this angle is. I'm thinking that eventually I'm going to have a tension force exerted along that line, so I'm going to need the angle to find its components. And if I look at this geometrical triangle here, I can see that the opposite side is 4 and the hypotenuse is 5. So the sine of this angle is 4/5. And if you do the inverse sine, I think you'll find that the angle is 53.1 degrees. The other thing that we might want to figure out, looking ahead, is how far from the wall is the cable attached? What's the other side of this triangle? There's a number of ways you could do it, armed with this angle. This is the adjacent side, and this is the hypotenuse. So you could take the cosine of this angle and multiply it by 5. Or you could use the Pythagorean theorem. This squared plus 4 squared has got to be 5 squared. No matter how you do it, you're going to find that the length of that side is 3 meters. So the authors give all the numbers to 3 sig figs. So we're going to begin a problem like this, like we always did for static equilibrium, and that is by drawing a nice free body diagram. Except we can't make a free body diagram that begins as a point, because this is a body that has forces exerted at different places. So I'm going to draw a line, and the line is not really going to be the beam. Rather, it's going to serve as a place where I can anchor the various forces that are exerted on the beam. Okay, so what's 1? Well, the easy one, the force of gravity. But where is it located on a beam that has mass distributed everywhere? Well, you're told that this is a uniform beam, which means that the weight of the beam is everywhere the same. So the force of gravity is going to be located at its center. Now the other force that's exerted on the beam is the tension force, and that's exerted here down at the end, off at some angle. We know the angle is the same as over here. And we know that the tension force is equal to 1,000 newtons. The other issue we have is, what about the forces exerted by the hinge on the beam? Well, I don't know exactly which direction that force pushes, but I could imagine that it has components. For example, I suspect that the hinge has got to push the beam upward to prevent it from sliding down. Of course, it might be the other way, but if I'm not sure, I'll just pick up and the math will work that out for us. But I'm also pretty sure that the hinge is going to be exerting a horizontal component of a force here to keep the beam from moving into the wall. So I think now we've accounted for all the forces, but I can see, looking ahead, that I'm going to have an x and y coordinate system. Look at these are both up and down. This one's horizontal. If I choose a coordinate system that's left and right and up and down, there's only one force I need to resolve into its components, and that's this one here. It has a y component, which comes from the opposite side of this little triangle. So ty is equal to t times the sine of the angle. And it has an x component, which now my diagram is getting a little cluttered, but tx is going to be t times the cosine of that angle. So I'm doing all right here. I have resolved this force into its components. So let me just one more time describe the forces, because my diagram maybe could be a little bit bigger. You should make a bigger diagram. Bigger is always better. So what do I have? The weight is acting down at the center of the beam. The cable pulls up and to the left at this angle theta that we figured out geometrically. So its vertical or upward component is t times the sine of that angle, and its horizontal component is t times the cosine of that angle. And then at the hinge, there are two components, a horizontal component and a vertical component. Now I have all the forces, and I have them all resolved into components, so now I have to apply the conditions for equilibrium to see where the answer to the question can be found. So I know that if I add the x components of the forces, I got to get 0. So what do we have for that? Well, the only two forces that have x components are this one and this one. And if right is positive, I would say that there's one truth of this system. So FH points to the right, TX points to the left. They got to add to 0. Without even stopping to look, I'll sum the forces, the y components of the forces, and get another truth. What do I have here? Looks like I have 3. I have the vertical component of the force on the beam by the hinge. I have the vertical component of the tension exerted by the cable, and I have the downward component, the force of gravity. So if up is plus and down is minus, it must be this. So there's a second truth. Now let's stop and see if I could just answer the question from what I have here. The question is to figure out what's the mass of the beam if the tension in the cable is 1,000 newtons. Well, I'm a little bit in trouble with equation 2 here because this is still an unknown. I don't know what the vertical component of the force on the beam by the hinge is. So this isn't going to give it to me. Maybe there's some information over here. I know the tension in the cable, so this would tell me what the horizontal component of the force is, but I need the vertical component in order to find the mass, so I seem to be short one equation. That's where you have to resort to the second condition for equilibrium. You have to sum the torques exerted on the beam and set that sum equal to 0. Now, to sum the torques, you have to choose an origin. So notice I made an xy coordinate system here, but I didn't put the origin anywhere. I can put the origin anywhere I want. I could put it here, I could put it here, I could put it here, I could put it where it is over here. But if you're smart about where you put the origin, you can generate a torque equation that's pretty easy to solve. Here's what I think. I'm going to choose the origin to be here. The reason why I'm going to choose the origin to be here is because any forces that are exerted at this point don't exert torques. In fact, about this point, there's only two forces that exert torques, the tension force and the weight force. And they got to sum to 0. Furthermore, I'm thinking that I'm going to very easily be able to get the torque due to the tension force because the y component of that force is perpendicular to a line that goes from the origin to the place where the force is exerted. That's our 3 meters. So here's what I would get. I feel like the tension force pulls the beam counterclockwise, so it's positive, and the mg force exerts a clockwise torque. So they got to give you 0. And all I have to do then is quantify what those torques are. Not too hard, as a matter of fact. The torque due to the tension force is the y component of the force. You see it's already perpendicular. So it's t sine theta times the attachment distance for the moment arm. And for the weight, its lever arm is half the length of the beam because the weight is located at the center of the beam. So that's the third truth for this system, but this one I can solve. Think about it. I got the tension force, I got D, I have L, and I'm asked to find the maximum weight of the beam. So that's not so hard to work out, as a matter of fact. It's 2T. So I did it quickly algebraically, but you may want to pause the video and confirm. But we're going to find out what's the maximum weight of the beam given the 1,000 max tension that you can get. So if you plug in the numbers here, I already worked through it, I get 533 newtons for the maximum weight of the beam, and that would correspond to a maximum mass, which is equal to the weight divided by G, like we've done before, of like 54.3 kilograms. So that actually answers part A. What's the maximum mass of the beam that we can support with a cable that can exert a maximum force of 1,000 newtons? The question does have a part B. So part B of the question is to figure out what's FH, the horizontal component of the force exerted on the beam by the wall, and what's FV, the vertical component. Well, for the sake of brevity, I'm going to let you figure that out because I think it's fairly easy to unravel at this point. The horizontal component of the force from equation 1 has to be T cosine theta, but you know T is 1,000 newtons and you know the angle. So that would tell you what the horizontal component of the force is. The vertical component of the force is going to come from equation 2. You know the tension, you know the angle, and now from the torque equation we figured the maximum weight of the beam, 533 newtons. So you can plug those numbers into equation 2 and get what the vertical component of the force exerted on the beam by the wall is. In any case, this illustrates the process. The process is normally to draw a picture that shows you the various lengths and distances and angles, and then to draw a free body diagram which shows the forces and the distances and the angles. On here, length represents a force in newtons. On here, length represents a distance in meters. So I don't advise drawing these forces on this diagram. Number one, it would get too cluttered. And number two, you might be confused thinking that somehow the length of the cable is related to the magnitude of the tension force, because they're not. Now, if I look back on my work, I see that the bottom part is pretty organized and neat, but I would probably criticize myself for making a diagram which isn't as clear as it could be. So let that be a lesson to you. Make a nice big free body diagram, because without the diagram, the solution is nearly impossible.